In the field of artificial intelligence, particularly with large language models, process reward models, or PRMs, play a crucial role in evaluating and guiding the reasoning process during tasks like problem solving. These models act as verifiers, checking whether each step in a solution is correct, which helps in scaling up test time computations for better performance. Traditionally, PRMs have been designed as discriminative classifiers, trained to distinguish between correct and incorrect reasoning steps. However, this approach demands extensive step-level annotations, which can be costly and time-consuming to obtain. This research introduces a novel approach called ThinkPRM, developed by a team including Mohammed Khalifa from the University of Michigan and collaborators from institutions like Mila, LGAI Research, and the University of Illinois Urbana-Champaign. ThinkPRM is a generative, verbalized reward model that verifies solutions by generating a detailed verification chain of thought, or COT. Unlike standard PRMs that require hundreds of thousands of labeled examples, ThinkPRM is trained on just a fraction of that data, specifically, as few as 8,000 process labels or even 1,000 synthetic examples, making it far more data efficient. The key innovation here lies in leveraging the inherent reasoning capabilities of large reasoning models, or LLMs. These models are fine-tuned through lightweight processes using synthetic data, allowing ThinkPRM to produce a step-by-step verification narrative. This method not only maintains interpretability but also enhances accuracy by enabling the model to think longer and deeper through the problem. In their experiments, the researchers compared ThinkPRM against established baselines, including LLM-as-a-Judge and traditional discriminative PRMs. For instance, on the ProcessBench dataset, a ThinkPRM model with 14 billion parameters, trained on only 8,000 labels, outperformed discriminative PRMs that were trained on about 100 times more data. This was measured using F1 scores, where ThinkPRM achieved superior results, demonstrating its efficiency. Moving to more challenging benchmarks, such as Math 500 and AIME 2024, ThinkPRM excelled in scenarios like best-of-n selection and reward-guided search. In reward-guided search on Math 500, a smaller ThinkPRM model with 1.5 billion parameters, again trained on just 8,000 labels, surpassed both LLM-as-a-Judge and discriminative verifiers. The figure from the paper illustrates this clearly, showing higher accuracy percentages for ThinkPRM as the number of beams in the search process increases. An important out-of-domain evaluation further highlights the robustness of ThinkPRM. On a subset of the GPQA-Diamond dataset, it outperformed discriminative verifiers trained on the full 800,000 label PRM dataset by about 8%. Similarly, on LiveCodeBench, it achieved a 4.5% improvement. This indicates that ThinkPRM generalizes well beyond the data it was trained on, which is a significant advantage for real-world applications. One of the standout features of ThinkPRM is its ability to scale verification compute effectively. Under the same token budget, it outperforms LLM-as-a-Judge by generating longer and more thoughtful chains of reasoning. For example, on a subset of ProcessBench, extending the thinking process up to 32,000 tokens led to an F1 score improvement of over 7.2% compared to LLM-as-a-Judge. This scalability is visualized in the paper's figures, which show how increasing the number of tokens enhances performance without proportional increases in computational cost. The researchers attribute this success to the way ThinkPRM capitalizes on the strengths of generative models. By repurposing open-weight large reasoning models and fine-tuning them lightly, they avoid the pitfalls of uncustomized LLMs, which often struggle with complex reasoning tasks. This approach addresses a key question in the field: how to combine the data efficiency and interpretability of generative verification with the high performance of specialized discriminative models. In practical terms, ThinkPRM could revolutionize how we handle tasks requiring step-by-step verification, such as mathematical problem-solving, code generation, or scientific reasoning. The paper emphasizes that by requiring minimal supervision for training, ThinkPRM opens up new possibilities for scaling test time compute in a cost-effective manner. To ensure transparency and reproducibility, the team plans to release their code, data, and models on GitHub, allowing others to build upon this work. Overall, This research underscores the potential of generative, long-caught-based PRMs to advance AI reasoning capabilities while minimizing the resources needed for development.